This video gives you a one-page tour of the Linux tracing landscape. Panel 1 talks about core frameworks, the tracing machinery built directly into kernel source. Two pillars sit here. ftrace, the function tracer, hooks into kernel functions, analyzes call graphs, and is engineered for low overhead. Alongside it are kernel trace points, static instrumentation points hard-coded into the kernel by its developers. The key word is static. They are placed deliberately in major subsystems and grouped by area, and because they are maintained by kernel developers, they offer a stable API and a reliable data layout that won't shift between kernel revisions. Both feed into a lockless ring buffer, the trace-fs buffer, which stores event records efficiently without blocking the producers. Finally, all of this surfaces to user space through syskernel tracing, the trace-fs file system. So the mental model is hook, buffer, and read. Panel 2 is about dynamic probes. Static trace points are great, but they only exist where someone put them. When you need to trace code with no pre-configured trace point, you reach for dynamic instrumentation. 4 tools here. K-probes can attach to almost any line or instruction inside the kernel. U-probes do the same thing but for compiled binaries and libraries in user space. F-probes are more specialized ftrace optimized mechanisms for function entry and exit tracing. And user events let applications push their own custom events into trace-fs. The panel also flags event histograms, the ability to aggregate metrics like latency directly inside the kernel, so you're not constantly copying raw event data out to user space just to compute a summary. Panel 3 is about eBPF, extended Berkeley packet filters. This is the new paradigm. eBPF lets you run small sandboxed programs inside the kernel without modifying kernel source or rebooting. The workflow. You write code in C, Rust, or Go, compile it with LLVM or GCC into eBPF bytecode, and load it via the BPF syscall. Inside the kernel, the verifier is the gatekeeper. It guarantees safe memory access, no infinite loops, and that your program can't crash or hang the OS. Once verified, a just-in-time compiler translates the bytecode into native machine code so it runs at full hardware speed. eBPF programs attach to a wide range of hooks, trace points, K-probes, U-probes, perf events, net filters, LSM for security, traffic control, and XDP for high-speed packet processing. eBPF maps are the shared memory structures like hash maps, per CPU arrays, ring buffers that let kernel and user space exchange data. Panel 4 is about end-to-end architecture. This ties the first 3 panels into one flow. At the source layer, hardware and software events originate from CPU, memory, I/O, network. The kernel produces events from schedulers, syscalls, drivers, file system. The tracing infrastructure layer like ftrace, trace points, perf, events, eBPF, plus elting, and system tabs help in collecting the data. And user space consumes them through tracefs, perf, tooling like bpftrace, and trace command or custom applications. Events are generated, captured by in-kernel substrates, and read by user space tools for analysis. Panel 5 is about use cases. Why this matters in practice. Performance analysis for latency and CPU hotspots, troubleshooting intermittent bugs, security and syscall monitoring, capacity planning, and production application profiling are some of the use cases. Takeaway is that this tooling is built in, low overhead, and lets you observe any layer with the right tool. So the panel 6 has some concrete first commands like listing trace points under syskernel tracing events, enabling function tracing by writing to current tracer, recording with trace command, profiling with perf, and try eBPF with a one-liner BPF trace script counting exec calls. To summarize, pick static when it exists, dynamic when it doesn't, and eBPF when you want programmable, safe, high-performance observability. Thank you.